Thank you for inviting me. It's a pleasure to speak at these technical conferences. I'm going to speak a little bit about making the electrical signals of the human body accessible to anyone who wishes to observe them. So you all know what this organ is. It's the brain. It's very complicated to study. It's so complicated that if you decided one day that, gee, I really want to understand how this, 1 kilogram, 300 gram mass in my head works, you have to go to graduate school, spend 5 to 7 years using advanced equipment, and the barrier to entry is just really high. So I was talking to Bruce, who's going to talk in a couple hours last night, that neuroscience and life sciences in general is kind of where computers were in the 60s, that you had to be a graduate student, you had to be a professor at a major research university, and you wrote a big grant from the NSF or the NIH, and you could buy a computer, and then you could, the sacred few with keys to the secrets of knowledge could use this technology. Neuroscience is sort of like that this equipment costs about $250,000 that my co-founder Greg Gage and I use for our graduate work, which really is upsetting to us because in a lot of other sciences like astronomy, mathematics, computation, electrical engineering, you can get started as early as you want, that the barrier to entry is very low. So we've been trying to do the same thing for life sciences. So we've been in operation for about 5 years, and we're taking the kind of advanced technology that you need government grants and that are frankly very hard to use, and making them consumer grade so that high school students and aficionados and amateurs can learn about how their own body works. Okay, it's important not only because it's one of the great mysteries of our existence, how does our brain work, but also it's because we're sort of in the dark ages when it comes to neuroscience afflictions. I'm sure everyone in this audience has a family member that suffers from a neuroscience affliction, be it dementia, depression, addiction, epilepsy, tumors, strokes. We really, when it comes to diseases of the brain, we really are limited in how we can treat that. So if we can make the tools that allow people to study the brain at an earlier age, we'll sort of accelerate innovation and allow the future scientists, engineers, and doctors and other creative professionals to be even better at what they do. Okay, so and another reason is that neuroscience and electrical engineering and computation, a lot of the talks in this conference are about kind of the ever-accelerating innovation in computation and communication technologies. And it always is sort of bittersweet for me because in the late 18th century in northern Italy, between Pavia and Bologna, modern neuroscience and modern electronics began with the famous experiments of Luigi Galvani, who showed that if he stimulated the leg or the nerve in a leg of a frog with a friction machine or a primitive condenser, the leg would move. And these were very influential experiments that people verified throughout Europe, which led Galvani to hypothesize that if electricity could excite the nerve, then perhaps the nerve and the muscles had their own electricity as well. And there was another gentleman from northern Italy, Alessandro Volta, the name probably is a little familiar to some of you, didn't believe that the tissue itself could generate its own electricity. He just thought something weird was going on when Galvani touched a metal tool to the salty interface of the leg, so he invented the battery. So the first battery was invented to test a hypothesis against the hypothesis of Luigi Galvani, who started neuroscience. So the first battery, like the battery in here, was due to this debate, and it was Volta's pile, voltaic pile, was a pile, una pila, of copper, salt water-infused cardboard, and zinc. And so neuroscience and electronics started at the same time, but neuroscience hasn't really advanced quite to the level that obviously electronics has, and why we can have conferences where we talk about all the new innovations in computer tech. All right, so there are 3 systems in your body that use electrical signals to function: the nerves in your brain, muscles, and hearts. So when we started, we wanted to show the electrical activity of individual neurons. You have 80 billion neurons in your brain that are communicating with each other by electrical impulses and neurotransmitters across the synapses. And this electrical impulse is not due to the movement of electrons like this, like that, like all the phones you guys are using. It's due to the movement of ions, so positively and negatively charged ions like calcium, sodium, potassium, chlorine. All right? So the electrical impulse generated by neurons is small, on the order of 1 millivolt. So to measure it, we need to amplify it. So we built these DIY kind of low-grade amplifiers, very simple, that could amplify the electrical activity from 1 millivolt to 1 volt. But the problem is the electricity is so small that's generated by neurons that you have to stick electrodes in tissue. So we can't, if we want to go to a high school and show the signals of the body, we can't stick electrodes in a student. So what we had to do is we went to our friend, the blessed, beautiful cockroach that has a nervous system like we do. And the nice thing about a cockroach is you can take a leg off, and the cockroach can still walk around with 5 legs. And where you can pull the leg off, this joint is very weak and it's like a defense mechanism, like the tail of a lizard, and there are stem cells at this joint that generate a new leg within 100 days. So it's a preparation that you can use to show neural activity. So students can put electrodes in the cockroach leg and they can see the firing of the neurons. What you see back there are the discharges of the neurons in the leg of the cockroach, and people can experience this and realize that the very same process of this impulse generation is happening in your brain right now, right now, and it's a very emotional, illuminating experience to see these signals for the first time. When I saw it for the first time when I was 20 years old, my life changed, and here I am talking about this technology 15 years later. Okay, so I'm not going to do any experiments on cockroaches because for every high school teacher that wants to do an experiment on cockroaches, there are 100 that would rather do experiments on the human body. And fortunately, the electrical activity of your heart and muscles we can do non-invasively with these sticker electrodes that I have on my forearm. So when you decide to move your body, your brain sends a command to your spinal cord, which sends a command to your muscle fibers, and the neuron talks to the muscle fibers, and the muscle fibers themselves discharge electrical impulses. And this impulse made by the muscle fiber causes the complex molecular machinery where actin and myosin slide across each other, and you get contraction and all that wonderful stuff of a human body in movement. So we can amplify this electrical signal made by muscles that is the beginning, the commencement of contraction, but I'm not going to do it in me. I'm going to do it in one of you. So I need a volunteer. This won't hurt. It's just a passive. So I can't really see that well, so I need help from a moderator to pick somebody. Just anybody, okay? Yeah, okay, you, in the flannel, yes. What's your name? Danny. Danny, okay. Ben, okay. Have a seat. All right, hi Danny. All right, I'm just gonna put some electrodes on your forearm. All right, so I'm gonna put signal here, and signal here. And so this is our little amplifier. And so this looks like a prototype because it is a prototype. It is the newest version of our muscle spiker box, and I'm happy to show it to you guys today because we actually have a Brazilian engineer who works for Backyard Brains, and he is currently in, excuse my, Ribeirão Preto, and he went to university at Barão de Mau. Yeah, so Max, we're doing this demo in front of all your countrymen, so it better work. All right, so here I'm gonna hook this up. All right, so I'm gonna put 2 electrodes here, and then, all right, so I'm gonna turn it on. Whoa, okay. Oh my God, all right, so contract, Danny, come with more force. Relax, contract. All right, so we are listening to the electrical impulses generated by the forearm of Danny, and we can actually see the impulses. So can I share your body signal to the audience? Okay, he is going to reveal his body to us. Okay, now contract. All right, so these impulses are the action potentials generated by the muscle fibers inside the forearm of Danny. So we're seeing these spikes are actually happening before contraction, but it's about 1 millisecond, so we can't perceive it. All right, so it's great to be able to see the individual signals of your body, again, to see that all his muscle fibers in his body are discharging electrical impulses, and we can do investigations, but we can also do interfaces. So what we have is a version of this amplifier, but it's hooked up to a microcontroller, and you can use this as a model of a neuroprosthetic, a brain-machine interface, and students and hobbyists can control robotics, video games, whatever their imagination can come up with the electrical activity of their muscles. So I'm going to turn off. Good, thanks, Max. All right, so I'm going to turn this off, and then I'm going to hook this up right here, and I'm going to turn it on. All right, so contract, Danny. All right, so it's a little boring, but relax, contract. But Danny is controlling the lights on this little circuit board with his muscle activity. So this first demo was actually done by a high school student in Chile. We work in both Chile and the United States. But we have the signal. We have the signal, so we can control whatever we want now. So for example, I collaborated with the theater group in Santiago, and the actor during the climax of the film was controlling the theater lights in his whole theater. So we could connect Danny to every light in this building, and he could contract and all the lights would flash. So it's cool. It looks really compelling. All right, so these little LEDs is kind of, okay, I can control LEDs, but we can also control this. So this is a little robotic claw, so all right, so just grab it. All right, so I'm gonna put some power to the robotic claw. All right, contract. Ooh. All right, we can reverse the direction. Relax. All right, contract. All right. No, it doesn't hurt. Okay. So yeah, so you can see these are just two simple interfaces, but we have much more things that you can control, and this is sort of a creative tool where people can control robotics and stuff with the signals of their own body. So it's kind of DIY, bringing the signals of your own body at your own disposition. All right, so thanks, Danny. All right, that's a gift. It's a gift. Yeah. All right. It's unstable. All right. We fear change. All right. All right. Okay, so I just showed the signals of the muscles, but now we're going to show signals of the heart. So your heart is a type of muscle, but it can contract without input from the brain, though the brain can, of course, control your heart. And so you all have seen this before, this electrocardiographic signal. It's a standard impulse, and every part of this impulse corresponds to a phase of the contraction of the heart. So we're going to do a demo where we record brain activity, but we need to test that everything's working by testing on the much larger signal heart activity. So I need someone to loan me their heart, and we're going to record the heart signals on the screen. Okay, you? Yeah. All right, and so we need Jose Alatrevido. We need the computer hooked up. All right. All right. All right. So we now are just looking at my computer, so have a seat. What's your name?
Luis.
Luis. Okay, so we're going to record the electrical impulses across your wrist, okay? All right. All right. So here we go. And then here we go. All right. All right. And then we have another amplifier that we're going to hook up here. Okay. All right. All right, so I'm going to hook this up here. There's a little bit of a lag, but the experiment should still work. All right. All right, so here we go. And then here we go. And then I'm going to connect this right here, okay? All right, so now we're going to connect. Connect. All right. Ooh. All right. All right. So, Luis. All right, so now we are looking at the heart activity of Luis. There is a little hill. Relax your hands completely. Okay, there's a little hill, which is the contraction of his atria. The big impulse is the contraction of his ventricles, and then that big hill is the preparation of the heart for the next contraction. You know, you can see it right here. All right, and then we can turn on a little beep. All right, so one moment. Okay. Just give me a second. All right. All right. The sound does not appear to be working. Doesn't really matter. All right. So anyway, we can see the heartbeat, but now we're going to go back to do something more ambitious. So can we go back to the slides? All right, we are going to try to record the electrical activity of Luis's brain, and show it live in front of all of you. And I've never done this before in front of a huge audience. So I've been working with the great AV people, and we're gonna try to do something innovative here at the Innovators Summit. Okay? All right. So I did the thing with the cockroach leg, so we can use the cockroach leg preparation to show the spiking of individual neurons, but we can try to see the activity of a brain. So if I wanted to show an individual neuron inside Luis's brain, I'd have to drill a hole in his head, and you know, he's guapo, I don't want to mess his head up. So, all right, but we can try to detect patterns, general patterns of brain activity. So I see a room full of beautiful Brazilians, and I see all this detail in your clothes, and your face, and your hair. So there's a lot of information processing happening in my brain. But if I close my eyes, all I see is darkness and pain. No, so when my eyes are closed, my visual cortex is entering a sort of synchronization, a sort of song where it says, it looks dark, it looks dark, it looks dark. And this song is sufficiently synchronous that we can sort of detect it outside the cranium. So an analogy is sort of like a stadium. If I'm outside a stadium during halftime and all the people are talking, I can't really make out any information outside of the stadium. This is like when I'm looking at you, when I'm talking, when I'm thinking about my presentation. There's so much information processing happening in my brain that we can't detect a pattern outside of the cranium or outside the stadium. But when everybody's singing the national anthem, a large group of you are doing the same thing at the same time. And like the person outside the stadium, you can sort of hear, though distorted, the national anthem. So this is sort of what's happening with eyes closed. And if there's a goal and everybody screams, this is sort of like epilepsy, and it's very, very dangerous. All right? So we're going to try to do this recording. And can we switch back to the data view? Okay, terrific. All right. So I'm going to put another electrode on the ground behind your ear. Okay, so I'm going to put one here. All right. And then we have a special brain headband right here. So I'm going to put it has a cockroach on it. All right, so I'm going to put this. All right, I'm not going to stimulate. I'm just going to record, so don't worry. Okay? All right, so then I need to improve the interface, so I'm going to put a little bit of gel on the electrodes here. Okay? I feel like I'm a hairdresser. So what'd you do this weekend? Okay, see, like, all right. All right, so did you feel the gel on both sides? Yeah. Okay, so cold gel, that's good. That means we have an interface. So I'm going to move the electrodes. Pardon, okay? So I need you to be totally calm, totally enter the flow. You're not in a room full of tons of people looking at you. You are relaxed, all right? All right, and the electrode does not fall off. All right. All right, so we're going to go back to the waveform view. All right. All right, so this may or may not be the brain of Luis. Like I said, there's a lot of information processing occurring in his brain right now because he's in front of an audience, he's looking at you all, he's thinking about what's going on at this they got my brain hooked up. All right, but what I'm going to ask him to do is close his eyes, and when he closes his eyes, we should see these ripples, okay? So, listo? Ready? Okay, close your eyes. No! Okay, all right. All right. All right. All right, so relax. All right, so these ripples are the alpha wave oscillations of his visual cortex. So we're seeing the activity of his brain untransformed, live and direct. I don't think this has ever been done before. So you're seeing the thing. Now open your eyes. Okay, and the signal goes away. Okay, close your eyes. All right, you all see those ripples? Yes? See? No? All right. So this is, okay, open. Okay, close. Wow, it worked. It worked. Yeah, see? Yeah. All right. All right. So, okay. Let me see if I can get this. Yeah, I can't get it. All right. All right, so can we go back to the slide? The slides? Okay, muchas gracias, Luis, por prestarnos tu cerebro. Okay, yay, Luis. All right, all right. Thank you. Nice to meet you. Okay. All right. All right, so when we talk about DIY neuroscience, this first experiment on EEG was done in 1934 with really expensive equipment, and this signal is very, very weak. It's very, very hard to detect this brain signal. We had the fortune to observe it here in this lecture hall. But I was actually working in a Santiago makerspace, and a bunch of artists wanted to record their own brain activity. I said, impossible. Most of the products out there aren't any good. But we did an experiment, and the signal was really noisy. But when I analyzed the data, we actually did see human brain activity, and we kept working on a prototype. And now it's reliable enough that we could show it in an audience. All right. So this all began simply as two graduate students who were kind of fed up with using all this expensive gear that they could never afford, and we started inventing this equipment, and it was really just a personal project, but people like you and professors and educators and entrepreneurs and people in the startup world around the world kept emailing us saying, continue in this project, it's really exciting, and 5 years later, this gear that I showed to you is in 75 countries, and we're continuing to build new interfaces to show any signal of the body that any of you want to observe, so thank you very much.
Tim, let's have a seat.
Okay.
And as always, we're going to have some questions from the audience. So if you want to formulate your question and be ready for it when it's time, please do so. So Tim, it looks like we're going to have a lot of fun here today. I took a look at your website, and I saw so many different experiments there. Very different and unusual, I would say. Who comes up with these experiments? Is that you, your team, a community?
Yeah, it's a mix of community engagement and also ideas from our team. So this is a short talk, but for example, plants can generate electricity as well, and I'm a physiologist of animals. I don't study plants, but we received a bunch of emails from plant biologists asking us if it's possible to do it, and so now we have experiments on Venus flytraps and sensitive mimosas. I didn't show an experiment where it's possible to control another human. There was a TED Talk in 2015 where my business partner used an EMG of one person to stimulate the nerve of another person so their arm moved. That was an idea of a science camp I was speaking at. They asked us if it's possible for one person to control another person, and so I spent a couple of weeks and we got that prototype working. So, and then sometimes just personal curiosity. This EEG thing was something I wanted to work on, and it really just took a push from a friend, and we wanted to impress our friends, and that's how it goes.
When you hooked that guy with the headband, I thought that you were going to make him sing and dance. And
yeah, that's with stimulation, but we don't have any stimulation gear for human brains yet.
So I also saw that you have these kind of sessions, educational sessions in different cities, right? How do you do that? Do you have, is it your own team, or do you have people, partnerships? How do you do that?
Yeah, so Lincoln Aldo invited me to give a talk here, and maybe he has an interest in biology, and he says, I know you don't live in Brazil, but maybe we can do something where I run workshops, and if we get along, then yeah, we usually send some gear, and we do have people in San Francisco and New York and Kansas City and in Santiago, Chile, who run workshops. Because a lot of the stuff is interesting, but it's not really taught at the high school, so there's this kind of knowledge gap that needs to be kind of bridged with an expert just explaining it. Like if you've never seen a microscope before, someone should show you a microscope, and then after you've seen it, then you can start using it, sort of like that.
Okay. And there is one particular experiment that I saw there, have those kits, right, that you sell on your website. And there is the robo-roach, right? Yeah. A very interesting one. Can you describe that a little bit? And, I have a follow-up question after that.
Sure. So that's actually funny, because the reason I'm here is because Lincoln in Buenos Aires a couple years ago saw the first demo, the first Bluetooth Roboroach. And I'm focused more on human experiments now, but when we started out, in grad school I would often read papers where people would control insects with stimulation of the antenna. So a bug uses its antenna to navigate, and so if you send electrical stimulation to the antenna, they'll interpret that as an illusion, as wind, and they'll move. But the thing is about academia, is you read the papers, but you never see a demo. You never see at a scientific conference, this is my invention here and it works. But in the tech industry, demos are critically important. Like if there's no demo, your technology may not even be real unless you're, so reading about these things in the academic literature, but never actually seeing it working is what motivated us to try to build our own. And then we started selling it as a kit. So it's one of our more controversial experiments, and I don't really do that many demos of it anymore.
Yeah, I saw that there's a lot of concern about these criticisms about using animals and all that, right? You respond to many of these criticisms on your website, right? But I bet that one question that might appear when you show these experiments with cockroaches is that if you can control a cockroach, you're not too far from controlling a larger animal. Right?
Exactly. So that's slippery slope. One of our other experiments is where one person can control another human. And that's because we're stimulating the ulnar nerve, which is this really accessible nerve. But it seems like if you've achieved the fundamental technology of controlling something, then it's just engineering to make it full control. And the thing is, if you actually saw the Roboroach, like some of you in the audience may have, it works for about a minute, and it doesn't even work that well. Like you push the button on your phone and the cockroach moves a little bit, so it works, and it works enough that it's real. But after a minute, he adapts and just ignores the stimulation because nervous systems adapt, that's what they do. You're competing with all these other environmental stimuli that the cockroach is receiving, so full control of the creature, I mean, I don't think we'll be able to do that. The Roboroach is basically done. Like, we're not doing any active development on it anymore. So.
All right. So is there anybody with a question in the audience? If you can lead the... Any questions? In the meantime, I'm going to ask another one here. So we can see that you're very passionate about education, and you do this for educational purposes. So can you mention other research or experimentation in this neuroscience arena that you believe can bring us advances in healthcare in the near future?
Okay, so it's sort of a sad joke that it's very, very hard to innovate in the field of neuroscience because the brain is very, very difficult to access, both physically because it's got a skull, and also chemically because it has the blood-brain barrier. So it's very, very difficult. But there is some exciting things going on with deep brain stimulation, where they can stick electrodes in the brain and stimulate areas to treat afflictions. So the most famous is deep brain stimulation for Parkinson's. It's now being used to treat depression, and there's also a new technology called optogenetics where you can insert light-sensitive proteins into neurons, and you can get millisecond control of individual neurons, but this is a genetic engineering technique where you have to modify the composition of the neuron by inserting genes, and so it's sort of a research technique, but there are people trying to figure out how to get it to work in mammals because it may be an effective therapy.
All right. Good. Is there any question from the audience? I guess people are getting tired. Oh, we will have one there, too.
Yay.
Hi. I would like to know, you mentioned the cockroaches, but how are you dealing with neuroplasticity?
I don't hear very well, sorry.
Yeah, can you repeat the question, please?
How are you dealing with the problem of neuroplasticity?
Yeah. So that's why the Roboroach only works for a minute or two because of neuroplasticity. So when this first, if you read the few papers on remote control insects in the literature, you always see this adaptation. And so it was originally funded by the Department of Defense. You know, if you could control a bug, it could like do reconnaissance. But it doesn't work that well because of neuroplasticity. So as an educational preparation, where it only works for a minute, but students can see, oh yeah, the cockroach adapts, cool, it's terrific. But to really, but you'll never really achieve complete control of this insect because brains learn. I mean, that's what we do, is we learn. And so you have to deal with that, which is what he referred to as neuroplasticity. So.
I think we have another question.